So we did we talked about the DAC, right? And like calling it a DAC is confusing sometimes because some people do call this a DAC. These are different things. This is data acquisition. So it's like data logging and keeping track of data. This is digital to analog converter. So if someone says the word DAC, just ask them what they mean. It's not very clear. So this was data acquisition. That's fine. Acquisition. And the top one is our famous digital to analog converter, which we said sometimes people call a D to A. D to A, even D arrow, D to A. So the whole point of this was to try and recreate an analog signal as closely as we could from just our digital computing language. And so you can get kind of close, right? You're not going to get exactly perfect analog again because the nature of analog is that you have basically an infinite number of steps in your signal. You have no space in between each step in voltage. So if I had an analog signal, something like this, when I recreate it digitally, it's gonna not be perfect. And how good an approximation it is depends on the resolution of my DAC, digital to analog converter, right? If I have a higher number of bits, I'm going to have more levels that I can split my signal into, right? Exactly as you saw with the analog to digital converter, except now we're going the other way. So, and the way it works, you have your digital to analog converter chip, for example. You're going to talk to it digitally. And again, we're going to talk about how you would do this later. So you send ones and zeros, and then it spits out your nice approximated analog waveform, again, with those little steps. And like with the analog digital converter, you have an analog voltage reference you can use. And this will define the full scale range of the analog signal you put out, right? So if I put 5 volts on this pin, I put 5 volts here, and my signal can go up to 5 volts and no higher. We also talked really quickly about something called pulse width modulation. And we definitely didn't do it justice. But the idea is essentially using one signal and turning that on and off really quickly with different amounts of on time and off time within the same cycle, right? And so the general principle behind this is that you're hoping that by sending this signal, and you can do this just with the GPIO, right? All you need is zeros and ones. So let's say my logic level is 3v3, right? That means 3v3 volts is equivalent to a 1, 0 volts is equivalent to a 0. Just with the GPIO, I can turn it on and off at different duty cycles, we call this, right? So if it's on for 0.75 seconds and off for 0.25 seconds, we say that that's a duty cycle of 75%. I can do this just with the GPIO, right? Just turn on and off at different percentages, different ratios. Essentially what you're sending is, you're hoping that your load interprets it kind of like an average, right? So you're hoping that what your load sees is actually something like 75% of 3.3. Remember, 3v3 is just 3.3 with different notation, right? And so this is kind of useful. Essentially what you can do is If you're controlling at a higher voltage, for example, you can do this to a motor, and a motor will see 75% of the voltage, or 50% of the voltage, or 25% based on your duty cycle. And its speed will change that way. So you can control the speed of your motor based on this duty cycle that you yourself are controlling, right? And so you can do a quick little speed algorithm where you can continuously vary this width, make it smaller and the motor will slow down, make it bigger and the motor will speed up, right? You can also do this, actually, it's pretty common with LEDs. So if I have my microcontroller, MCU, I can turn a switch on and off really quickly with this varying duty cycle. Let's say this is my switch. For those of you in the electrical lesson, this is your MOSFET, right? But we can just interpret it as a control signal. So this is my pulses. And it's opening and closing this switch at the duty cycle that we specify, right? I swear this is an arrow. Okay. So in this case, when we're sending a 1 or a 2.3, we're closing the switch. When you send a 0, the switch opens up again. And we can put here is maybe something like this. Power. This is an LED, so a light emitting diode. And usually they're drawn with these little arrows as well to show this is light. If you ever were confused, that's literally how they quantified light, which is cool. So the idea here is that when this switch is closed, right? When the switch closes, then there's a path now for current to flow from power through the LED to ground. And when there's current flowing through an LED, then it's going to turn on, right? Then you have light emitting from that diode. Now, if I'm sending a 0 at that particular point in time, the switch is open. So the switch would look like this, open. Then there's no path for the current to flow, right? Current stops because there's nowhere for it to go, and the LED would turn off. Now, it turns out that, for example, let's say I'm sending this at a 1 kilohertz frequency. What that means is that my cycle time, so this is 1 cycle, right? This repeats forever. This is happening 1,000 times a second. 1 kilohertz literally means 1,000, 1 kilo, cycles per second. So the hertz unit is 1/second, right? What that means is that every cycle takes about 1 millisecond. So if I'm sending a signal at that frequency, and let's say that I have a 75% duty cycle, so it's on for 3/4 of the time that it's off, my LED brightness will actually be 75% bright. This is cool because now with just 1 pin, right, and it's not an analog pin, right? This is digital. We're just turning it on and off at different ratios, at different speeds. We can literally control the brightness of the LED. So if we bring the duty cycle now down to 25%, right? So we're 25% duty cycle. So what that would look like is something like this, right? So it's on for 25%, off for 75%. Then the cycle restarts. On for 25, and then off for 75. And the cycle restarts. On and on and on, right? That's 1 cycle. If I do this, now my LED brightness will be 25% bright. And so if I want to create like a cool little pulsing animation of the LED getting brighter and then dimmer, then brighter, then dimmer, you can guess that all you'd have to do is vary this width, right? Change it from 25% up to 30%, then up to 35%, and keep ramping slowly. And then you're going to get an increasingly bright LED, and then increasingly dim LED as you go down. So that's the power of PWM, pulse width modulation. Basically, you can get your loads to sort of see a certain percentage of the full scale, right? Instead of just my load seeing 3.3, 3.3, or 0, it's seeing almost 75% of 3.3, right? That's sort of the intuitive way to interpret it. It doesn't actually happen like that. You're not actually giving it 75% of 3.3. If you were, then there would be no need for digital to analog converter, right? But this is sort of the general principle. You're just turning it on and off really quickly and hoping that the load doesn't notice, essentially. So this works with motors as well. And it's sort of the fundamentals behind variable speeds in a motor, variable brightness in LED. This is a really good way to achieve that. Any questions? Cool. Note that we have no specific control here really over how much current we want through the LED, right? All we're doing is kind of visualizing a certain amount of brightness to and correlating that with some duty cycle. And it's all kind of vague, right? You can try one duty cycle and get a certain brightness, try another duty cycle and get another brightness, but it's very dependent on your observations, and you don't get a very good control of the current through that LED. So now that we have a good understanding of why I'd use PWM, and also review of our DAC, we'll talk a little bit about an application of the digital to analog converter. This was our application of PWM, but now we'll do a good application of the digital to analog. So what we're going to do is look at a interview question. Bum, bum, bum. So good luck, everybody. Start. Okay, I'm just kidding. So if you're working in embedded, the real truth is you're going to have to understand the electrical system around the embedded system. Mostly because everything that embedded is going to do is going to impact electrical, and it's going to act through an electrical system, right? That's how computers actually interact with different systems. They turn on and off voltages, control other components. Notice here, this is a digital to analog converter, right? This is an op amp. This is an LED. Go op amp. LED. Some MOSFETs here. And this is a linear regulator. So I'll just write it on the side. Regulator. So hopefully you guys find some of these components familiar. Oh man, regulator. Right, don't worry about that. Especially for the ones of you who've been in the electrical lessons, Jared's talked about some linear regulators there, as well as these MOSFETs here on the right, these guys. And we've been talking about digital to analog converters, which is great. So the story behind this is an actual interview schematic or question that I got asked sometime in third year, I think. And spoiler alert, I did not get the job. So I wasn't able to answer these questions. Or I tried and I got some, but not all of them. And they ended up not giving me the job. So this is for an electronics and embedded position as a co-op. For a company called Synapse Consulting. So they're an engineering consulting company in Seattle and San Francisco. And apparently people really love their co-ops. You get a lot of responsibility designing parts. And so they kind of really want you to answer some questions in the interview. And I was actually in China at the time when I got this interview, and so because of the time difference, I had to do it at like 2 a.m. I think, and so that also didn't help at all. So I was very sleep deprived. Not that I would have answered it correctly anyway, not sleep deprived, but very tired. And so like the very first question was, so if you were a superhero, what kind of superhero would you be? One of those ones. And I was so tired at that point that I really didn't care anymore. And I think I said I wanted to be like the Cyclops guy from X-Men, where like he just takes off his sunglasses and he has lasers shooting out of his eyes that destroy everything. Um, and in hindsight, I realized that's not a very good answer for an interview question for someone who's trying to hire you. So I'd recommend not to do that. But
What's your answer now?
probably still the same, to be honest. um, yeah, so this is the question, and we'll start working through it. So on the right here, you have some circuitry. You have our DAC in the middle. You have a linear regulator. And this is very similar to something you'd see in real life, right? This is an actual application of what we've been learning and something that the company actually had in one of their products. And so this is what you would see in industry as well. So let's go to number one. Just one quick thing. So sort of the general flow here is kind of from left to right in this particular schematic. So these things here, although you may not recognize them right now, they're pins for digital communication protocols. So something called SPI. And we'll talk about it in another lesson, but that's essentially where your embedded control is coming from. So off this page is a microcontroller that's sending commands here, right? And these commands are going to control what's happening through the rest of the system. So first question, what does analog output U2 Vout A control? What voltage or current is being controlled? So I'm going to let you guys kind of guide me through this. And there's no need to have the right answer, right? If you're asked an interview question like this, I'm not expecting you to give me bam, 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 all four answers right away. What I would want to know as an interviewer is, can you think, right? Can you logically step through some steps and have some deductive process for coming towards the answer, whether it's right or wrong? And so for this interview question, I'm going to start picking on people. It's going to be fun. But totally easy, right? All you want to do is kind of walk through, what are you seeing? What do you think might be on the way to the answer? And sort of just explain your thoughts verbally. So what does analog output U2 Vout A control? Let's start with Raphael. Why don't you walk us through this?
Okay. Well, I don't know what the triangle wave on the right outside it. I don't know what that is, but
This thing?
yeah.
Okay, that's okay.
But I think it leads to like that branch of resistors.
Okay, I like
So,
that. Vout A is here, right? Yeah, so you said it comes through here and goes this way, right?
yeah.
Okay.
I have no idea.
Okay, that's okay. What do these sets of resistors look like anything familiar to you?
Probably a voltage divider.
Nice. That's a great word to say. So voltage divider, that's exactly right. Voltage, we don't need an E, it's okay. Divider. Nice. And why do you use voltage dividers usually?
To step down the voltage for the op amp. I think.
Beautiful. Yeah, no, that's exactly right. So what's happening here is some voltage is coming out and it's being stepped down, right? So how is it being stepped down? Like, let's say I had a voltage of, just for argument's sake, 10 volts was here, right? I had 10 volts here. What would the voltage at the output be? How would we do that?
It's like V out equals V in times R, like R5 over R8 plus R5, something like
Out equals. Can you say again? Vn times.
that. R5 over R5 plus R8.
Okay. Anybody want to tell us if this is right or wrong? Maybe John.
Give me a second. I don't think that is. Oh, I think that is right. Right? No, it should be R8, not R5 on top.
Yeah, I think probably R8 on top.
Am I wrong?
That's right.
Sounds
Yay.
more.
Cool. Yeah, you can sort of remember by knowing which one's on top because you're basically seeing what
Equals ion.
voltage. Yeah, that's true. But also, so like the voltage here
Mm-hmm.
is referenced to ground, right?
Mm-hmm.
So that's the voltage across R8. And that's what you're going to get on top.
Mm-hmm.
Cool. So can you do that math for me? What voltage would that be on the output if our input was 10 volts? Can you give me that, Raphael?
It's something like 2 volts.
2 volts. Can someone confirm for me? I'm flying blind, no calculator.
I think that's right.
Sorry? Cool. Okay, so essentially you've stepped it down by a factor of 5. Is that right?
Yeah.
So went from 10 volts down to 2 volts. Cool. And we don't know if it's 10 volts actually at this point. We just guessed for the sake of understanding. But let's clean this up a little bit. So we're working our way through the interview. That's good. So far what you've said is some signal is coming out of this thing, right? We don't know what this kind of guy is, but we know it goes into a voltage divider and it steps it down by a factor of 5. So that's really good information to bring up in the interview. You really want to make sure that you're talking through it and kind of walking through your thought process. So let's just write here. I'm going to write 1 over 5. Okay, keep walking me through. What happens next?
It's controlling. So it's going through the op amp and then controlling some sort of MOSFET.
Okay,
and
nice.
so there's a white LED on top, so it's probably giving like, I don't know, a sign that the system is on or some sort of test.
Okay. So I don't know. Somehow I accidentally deleted all this. But yeah, that's exactly right. This is a MOSFET. This is an op amp. And this is an LED. And we don't really know what the LED is doing, like what the purpose of it is for. Yeah, it could be indicating that the system is on or some kind of test is running, or indicating that it's passing a test or failing a test. That's true. So that's good. Anyone else want to take a stab at what's happening here? Like, what is the question is, right? What's the question? What does analog output Vout A control? What is it actually impacting and influencing? How about for us?
Shit, 1 second.
So we have a voltage coming in, right?
Okay. So we got an op amp output is feeding out to a MOSFET, an N-channel MOSFET,
Nice, N channel. That's good to point out.
which controls the LED coming from. So this LED basically says we have the desired voltage for output A.
So you're saying if output A is active with some
Oh,
voltage, then
sorry.
this LED will turn on. Is that right?
If that's active, as well as the other MOSFET, which is the enable button.
Nice. Good spot. So this is coming. Usually when you see these two arrows on a schematic sheet, that means it's coming from a different sheet. So from somewhere else in the system, likely from your microcontroller. Very good observation. This is definitely something you should be pointing out. This is the enable, right? This is the signal that tells us whatever this whole op-amp thing is doing. This enable will turn on this MOSFET and actually allow things to start happening. So if this is off, if this is sending a 0 volts from a microcontroller, then nothing's going to happen. And so it's an enable, and you'll often see them in a lot of different systems. It could be for, this one is for this LED, but for other systems it could be for a motor, it could be for some other sort of actuator, or even for a sensor system to have that enable and safety in place. All right, that's good. But the real question is, what voltage or current is being controlled here? So you're talking about sort of the LED and you jump to the enable, but what voltage or current is being controlled?
Is it the LED's voltage and current?
It's only one. Remember, this is an OR.
Oh.
You got to guess one of the two, eh?
Is it VCC? Like LED VCC?
Yeah.
That is a good question. Or sorry, good answer. Good response. Okay, how would it control LED VCC? This was V out A, right?
The enable is on, and then the voltage is flowing. Then it compares LED VCC at the negative terminal of the op amp with V out A.
You hear what you're saying?
Or like on the negative terminal of the op amp
Here?
at the minus, yeah.
Where is this connected to LED VCC? Like this?
Oh, no, I guess maybe not. I thought just maybe the voltage wouldn't change from the top to the nodes. No, but it would. There's stuff. Yeah, I don't know.
So no, that's okay. Yeah. I'm glad you sort of walked through what you're thinking. That's exactly the kind of thing you want to see in an interview, even if you're wrong or right. But yeah, this is actually power to the op amp. So all that does is it turns it on, right? It allows it to operate. This is not going to interact with any of these three signals that the op amp deals with on input and output. Some of this down here, this is just ground for the op amp. So to be clear, these guys just turn on the op amp, and then the actual signals happen here. Courtney, thanks for asking. LED VCC, the way it's shown here is as a power source. So similar to how we would draw, for example, like if I have a DAC chip, digital to analog converter, for it to turn on, it actually needs a little bit of power. And so usually we show it either like this, sometimes it's a little arrow on top, but that's where we'd put like 5 volts, for example. And that's what would actually turn on that component. And in this case, we don't know what LED VCC is. That's actually one of the questions we're going to answer later. We don't know what it is, but we do know that it powers both the op amp and this branch, right? So the hot question for debate right now is, what is the voltage or current being controlled? So far we've said LED VCC, which I have not refuted, but I also want to understand how it would control LED VCC.
It's current, right? Because
It's
LED
current.
VCC is just solid. It's always there. So your VCC. But what's actually being controlled is the flipping of allowing current to be flown from LED VCC to ground. Depending on what that pin is going to output, it's going to give you enough to either turn on the MOSFET or not at all. Is that right?
Yeah, that is almost exactly right. Well done.
Could you
So,
could you say something
please.
like it changes the LED's voltage drop across it as well?
No, it can't, because it's like voltage drop of LED is constant. It's not like a PWM pin or anything. Like it's gonna be dimmed or light or brightened.
See,
Andre, you are crushing it. Good job.
Mr. Electrical over here.
Let's go. Okay, so a couple things Andre said. Let's go backwards. So he said that the LED will have a fixed voltage drop. It's absolutely true. So this is given to you in the datasheet of your LED. We don't know here, so this is just for the sake of understanding, and it's not super important, but it will have some voltage drop. It takes some voltage to actually forward bias this diode, so to actually let current flow through. If this condition is not met, then your diode will not conduct. You won't have any current through the LED, and you won't see any brightness or any light coming out. So for a wide LED, oh god, maybe 2 volts, maybe a little more. Some go as high as 3.3 volts to turn on. There's usually blue ones. But for green or red, usually you're going to see 2 volts drop across there. And that's going to be fixed. That's not going to change based on what's happening here. Another great observation. LED VCC is solid. That's absolutely true. There's nowhere here where that voltage is being changed or modified by the input signal. That's a power supply, right? It's a source that's coming in and giving power. Same way that it's giving power here and giving power here. That's the same idea as if we just had a 5-volt rail that we're using to power the DAC or to power the LED, right? Then the third thing Andre said, current. That current is exactly what's being controlled. And remember, the current through an LED is proportional to its brightness. So we are actually controlling exactly how much current. And remember before we even got to this, we talked about how you could PWM a MOSFET and kind of vaguely control the brightness. In this case, we are literally controlling exactly how much current to the milliamp is going through that LED. So we have insane precision and control of this brightness. And we don't exactly know what the application is for the consumer. So we're not sure if this is just a light on like a wearable device that this company is selling that just blinks on and off at different brightnesses. We don't know if it's some sort of optical application where the brightness of your system is really critical to the measurements taking place. But we do know that they want a really good control. And so V out A finally figured this one out. Check mark. Well done, everyone who got us to this point. The current of the LED is being controlled, right? And indirectly, what we're controlling is the brightness. Okay, that's good.
Hold up. I'm confused. How does it control the brightness? That went over my head.
Yeah, we're gonna get there. Cool.
Is it too
Sounds
early
good.
to ask what's the point of the op amp?
No, definitely not. We're gonna get there as well. We're really close to that. It's gonna be hard to explain that because it's not something we see a lot. But I'll do my best. Definitely not too early. Any other questions? Let's just get a quick log of them and then we can walk through.
Yeah, I guess that'll be explained with the op amp thing, but just like how different V out A would affect um, what we're doing with the LED, because all we need is turn on the gate for the MOSFET, right?
Yeah, that's how I understood it too. I thought it just turns on and off. But I guess that'll be answered in question 3.
Perfect. Great question. Why do we care about this? Why do we care about this? Why don't we just turn this on and off, right? Like just turn on for bright, turn off for not bright.
Yeah.
So one is if you just turn it on and off, you don't get control of brightness. 2 is if you try and PWM it, you're not going to get that precise control of brightness. You're just going to kind of get a visual gauge of bright or not bright, kind of dim. And we're going to explain exactly how that brightness is controlled through the current soon. Good questions. Anything else? All right. So what is the transfer function relating V out A to the parameter being controlled, which we found out is the current through the LED, right?
Fuck. What?
So can someone remind me what a transfer function is?
I'm in the class and I can't tell you.
Yeah. It sounds scary and stupid. And like in class, we have some equation. Faraz, do you have something?
Yeah, is it to do with filtering?
No, but that's a great. Filters do use a. Oh, I guess almost everything does, but they're mentioned a lot in filters for sure. That's a good observation, actually. Usually
Is it
in. Yeah, Mahmoud?
input over output?
Yeah, nice. So
So I remember one thing from that
good
class.
job. So all a transfer function is, it sounds fancy, and like I said, in class you're going to do with a bunch of equations and stuff. So all it is a box, right? All a transfer function is a box. It's a box that relates your input to your output. So if I put in some input to my box, right, some input, and in this case it's V out A, right? I'm putting some voltage in. What am I getting as the output? Right? And in our case, physically what this transfer function is actually this whole cascade of circuitry, right? Our transfer function is everything that comes after V out A. So this resistor, this voltage divider, this op amp, this MOSFET network, this LED, all of those are hidden inside my transfer function box, and they'll represent the conversion from V out A to the current being controlled here. All this is a box, and often how it's represented is usually you have to kind of look in the Laplace domain and do a bunch of weird transforms. Pardon me. Do a bunch of weird transforms, but we're not going to go through that today. But essentially, it's a box, right? It relates input to output, and in our case, output is, call it I out. Okay, maybe I LED, since that's a current that passes through the LED. I LED. Okay. So what we're going to do is figure out exactly what our transfer function is, and essentially, how you can view it is, if we call our input I and our output O, and our transfer function, let's call it TF, or maybe just one, just T. Then very roughly, a little bit conceptually as well, I times T equals O. Right? So to find the transfer function, I think Mahmoud said input over output. I think it's output over input, actually. Correct me if I'm wrong.
No, you're right.
So that's all. Am I right? Okay. Thanks. So that's all it is. Transfer function is the ratio of output over input. And all it really tells us is how they relate, right? And what it means is that we're going to have a really good relationship between V out A, and that current, right? and we asked, like, why do we even care about V out A? Why don't we just turn it on and off? Well, we're going to see exactly how V out A will impact that current by finding the transfer function. So this is a little bit tricky, to be honest. I thought it was hard in third year in an interview. But it's definitely possible to do, and it comes a lot from sort of recognizing different components, different little sections of circuitry. And so you have to have experience.
What
Any
company
questions,
is this again?
Andre?
What company
Say again?
is this again?
Synapse.
It sounds fun.
Yeah, this is engineering, right? So you're going to work with your embedded controls
I just
to
figured.
generate. Say again?
I just figured it out.
Yeah. To generate V out, right? And you get to control it, and that's going to influence the brightness. And you're going to have really good control from your embedded system over like this physical output. Do you want to enlighten us, Andre? What have you figured out?
What? Oh, just the rest of it.
Yeah? Okay.
But I'll let other people do the thing, do the thinking.
Does anyone else want to guide us through? Jared?
No, I want to see Andre's.
All right. Let's hear it, Andre.
Fuck. Okay. Oh, see, the only thing useful about what you should effectively see useful from the op amp is that it has a gain function, and that gain function is our basically transfer function going through from the input and the whatever that drives it in the output. What's the gain function? I can't remember. Let me look that up.
Raphael already helped us a little bit. He told us that V out A coming here is stepped down by 1 over 5, right? We went from, if we had 10 here, it'd become 2. So we know that part of our transfer function is going to be this 1 over 5. We know we're stepping down whatever we spit out by a factor of 5. Right, so that's one part, and that's good. Now there's kind of this whole other part. It's kind of tricky.
That looks like an integrator circuit using the op amp.
Yeah, that's
believe you.
interesting observation. Correct me if I'm wrong, but and why do you say integrator?
The capacitor positioning on this non-inverting tying the inverting pin to the output, I believe, is the integrator.
This little C13 you're saying?
Yeah.
Cool. So yeah, that's a good hint as to the integrator aspect. And all that does is it sort of adds up the voltage over time. But we actually don't need it to get the transfer function, interestingly enough. It's a little bit of a red herring here.
The capacitor?
Mm-hmm.
Isn't that just for a filter?
It's also used sometimes for something called feed-forward control. So it makes the gap very quick between these two pins. If you remember, capacitor likes AC, right? So AC passes through it, but it blocks DC, right? That means that any quick changes in the signal really quickly, those AC components will pass through the capacitor and help the control sort of react in anticipation. That's called feed forward. But again, that's not important for now. You can kind of do this whole thing ignoring that this even exists, to be honest.
So what's screwing me up is that there's no resistor in the bottom side. That entire that negative end of the op amp, I usually remember having a resistor there, and that's what drives the input output gain. Like your input's what Raphael was talking about, and that was golden, but what's a good going through depends on That circular pattern.
Mm-hmm.
So whatever is going through R7, then R11, and going back into, well, I guess we're just going into R11.
Yeah.
This is 0 actually. What the fuck? Hold on, I'm confused.
So it's hard to know unless you've kind of seen it before, but this is actually a pretty popular circuit. You can actually do it even without the feedback path. But you put your signal in here. This controls a transistor.
Very. Buffer.
Anyone know what this is? This is actually a constant current circuit. Yeah, Jared? I may have spoiled it from you.
No. Yeah, I was going to go because that basically is a buffer system, buffer configuration.
Kind of. I think a buffer is.
Buffer's the other way, isn't it? Like
Buffer connects straight here, right?
Yeah, it goes directly.
Yeah, so that'd be a buffer. But this is a constant current circuit. So essentially, what you're doing here is you're maintaining the current in this path, no matter what's happening with your load, right? And it's super cool because essentially if you were to try and control the current in a path, you'd need to switch between different resistors, right? And maybe use something like V equals IR, so if it changes the R, the I will change. And usually we have control over voltage, right? Remember Jared has talked about linear regulators and buck converters, so we know how to sort of regulate those and change voltages at will. But changing current isn't something that is as fundamentally easy or as intuitive. And so what actually happens here is you have the idea is that you're controlling this transistor in its linear range. You're not actually using it in saturation. So it's not actually being used as an on-off switch like you normally use them and how we enjoy them usually. So oftentimes we use MOSFETs as on-off, and that's cool. Probably 90% of the applications are like that. And that's what you use them in something called saturation mode, when your gate voltage is above the threshold. But in our case, we're using it in linear mode. And so what that means is that based on the voltage we're putting at this gate, we're changing the resistance of the MOSFET. And so in this mode, it's actually acting almost as a variable resistor based on the voltage that we're giving the gate. And so as we change this voltage here, it's either going to increase in resistance or decrease in resistance. And guess what? V equals IR, right? Like we just said, we have a constant V. We have RR, which is 10 plus this variable resistance. And so I equals V over R. If we get to change R, we get to control I. That's essentially what we're doing here with this whole circuit is about variably changing this MOSFET through its linear region. So the next question is, how do we actually regulate a constant current? How would we do that? It's actually pretty cool. It comes from properties of an op amp. So an op amp will do whatever it can on the output to try and bring its two inputs together to be the same, right? It doesn't like having a plus and a minus that are at different voltages. And so the bigger they are, the more difference between them, the more strongly it's going to send out a signal. If the difference is very small, if these plus and minus are 0 volts in difference, the exact same voltage, then it's going to send out almost nothing through here. It's going to maintain what it was doing before. So think about it this way. I have my op amp. I am forcing a voltage on the plus pin. This is the voltage I've forced to be here for my V. I say I want the plus pin to be at 3 volts. I don't care. What the op amp is going to do, especially in this configuration, it's going to look at its minus pin, and it's going to say, okay, what voltage are you at? Oh, are you at 0 volts? Okay, I need to send something to my output to change that. Now take a look here. Let's say our minus pin, let's say it's at 2 volts right now. And this was 10 ohms, right? This automatically controls the current in the path, right? You have a voltage across the resistor, straight to ground. If you just do V equals IR across this whole resistor, you're going to get the current flowing through this resistor, which is going to tell you the total current flowing through the path. So what's the current here? I is equal to 2 volts divided by 10 ohms. 0.2 amps, right? Now remember, our op amp wants to drive its output to force these two pins to be the same. So it's going to change the resistance of this MOSFET. And that's going to cause this voltage to start increasing up until 3 volts. When it hits 3 volts, the op amp's going to check its plus pin. It's going to check its minus pin. It's going to say, hey, there's no difference in between them. That's great. I can keep maintaining this at what it was before. I don't have to actively change anything. So essentially what you're doing is, with the voltage you're forcing on the plus pin, you're literally forcing that voltage at this node. Because your op amp is going to drive this variable resistor to change its resistance, therefore changing its voltage drop, until the voltage at this point is equal to the voltage at this point. Does that make sense? And what that means is that when the voltage at these points are equal, I now have a direct control over the current in this path. And that is because I have direct control over the voltage across this resistor. Right? If I get to control the voltage at this point, and this is 10 ohms, if I get to control this, if I get to control V, I know R is 10, then I get to define the current flowing through the resistor. And so the whole point of this op-amp feedback network is to provide a way to control the current across this resistor, which actually ends up being the current flowing across the whole path. And the reason that current doesn't break through this path and flow this way is because the input of the op amp has an insanely high resistance. They call it an input impedance in the mega ohms, maybe higher. So current's not going to want to flow this way to this high resistance. It's going to keep flowing in this path. So with whatever voltage I have here, I have a direct way to control the voltage across my resistor, and therefore the current through my load and my resistor. Questions? So in this case, my current would be 3 volts divided by 10 equals 0.3 amps. Andre, does that make sense?
Oh yeah, this is really cool.
Very
Jared?
sick.
Yeah, makes sense. Yeah. This is actually what I had to build this circuit once. I actually put it in my capstone. Is Samarine here? Is Samarine in this call? In our capstone, we use this circuit actually for brain stimulation. So what you can do is, not recommend to do at home, by the way, but you can actually create a circuit and pass it through your brain to try and stimulate different parts of it. And you can imagine in that application, you're going to really want to know what your current is. You want it to be as constant as possible. If you go too high, you're going to start feeling a little heat on the scalp. It's going to start burning a little bit. So you really need that current to be constant. And so we put this circuit in a little PCB that fits in the headset on your head and puts current through your skull. TMS is a great question. It's not TMS. It was actually something called TDCS. So it's transcranial direct current stimulation. So you actually had electrodes pasted to your head and current flowing through your brain. TMS is transcranial magnetic stimulation, and so those use magnetic fields to generate current, so no actual direct contact. But you can imagine, so same circuit, right? I control the voltage. Yeah, TDCS isn't as, hold on, my doggo is complaining.
Gabe, you muted.
Thanks. So I control the voltage, which forces that exact same voltage to be here, right? Which allows me to have a direct control over the current. But in my application, I had the human head was here. Right, and then we went to 12 volts. And you can imagine not everyone's head resistance is the same. And based on where you place your electrodes, your resistance is going to change as well. But by creating this constant current circuit, it doesn't matter what the resistance of the head is. It could be anything. Like, so it was usually from somewhere from 3 kilo ohms to 6 or 7. We still had control over this voltage, right, which defined the current. So no matter what load resistance we had, we could always control that current to a constant 2 milliamps, which is nice.
I have
So-
a question.
Please.
How fast does this process happen? Like it's self-adjusting, right?
Yeah, exactly. It's
So how fast does it like self-adjust? Is it like instantaneous or
yeah, basically.
okay?
I think it's sub-millisecond. So it obviously depends on how fast your op amp is. I don't know why I drew a line
Huh?
like this. It depends on how fast this op amp can react to the inputs
Oh, okay.
being different and then adjusting this gate. But usually it's really, really fast.
What
Yeah,
if like you had like a very you're like instead of a head, what if I can't think of anything, but it's like it would still keep the same voltage. I mean current going through then?
yeah, there's a limit as to what it can be. Essentially, it depends on your voltage supply. You can imagine, right? If my head is suddenly 100 kilo ohms, well, after a certain point, I'm not going to be able to push the current I want through it because it's too high resistance, right? So if I actually had 2 milliamps going through a load that was 100 kilo ohms, what would that voltage drop be across the head? Well, it'd be V equals IR, like we've used every time, right? So it'd be 2 milliamps times 100 kilo ohms. So that's a voltage drop of about 200 volts, right?
Woo.
Yeah. Newsflash, we don't have 200 volts to drop across the head. We only had 12. So this has limitations based on how much voltage you have and how much resistance your load actually is. So obviously you can't control any amount of current you want through anything. It's going to depend on the load, but you'll quickly realize if you need more voltage available.
Okay, thanks.
You're welcome. All right, so it's been an insanely long-winded explanation. Any questions from anybody? Raphael? Does this make sense to you?
Just about how the current doesn't depend on the like the head or the load.
Yeah.
I don't get how that works.
But yeah, good question. So essentially what we have here is we have a path, right? So you can forget all of this stuff for now. We have a path, right? So we have some voltage. I apologize for not being very succinct. But some voltage here, right? Okay, let's give it an actual value. So like 5 volts. And do you agree that there is a path here for current to flow?
Yep.
Okay, let's give it ahead. So this is load. In our case, it's an LED, right? It's an LED. Now, by some system of magic, that magic that we had, you get the chance to control the voltage at this pin. So you get the chance to say, I want to define the voltage at this pin. And because I know that the resistance from here to here is fixed, it's my resistor, 10 ohms. If I know the voltage drop across my resistor, and I know that it's a certain resistance, well then by our favorite formula, I can calculate exactly how much current is flowing in this path. Right? And by virtue of how series circuits work, because this resistor is in series with this LED, that same current is flowing through this whole thing. So if I can calculate the current flowing through just the resistor, I've been able to calculate the current flowing through the whole LED path. Does that make sense?
Oh, okay, yeah, it makes sense now.
Cool. And the whole assumption and premise we had to this was that we're able to control this voltage, right? And the way we did that is through this op amp. So now take a look at our original circuit. The op amp wants these two inputs to be identical. So it's going to drive the output, control the gate of this MOSFET as a variable resistor, essentially. And that resistance is going to force these two pins to be at the same voltage, right? And look at this. This pin is connected to the top of a resistor, 10 ohms. So what we're literally doing here is taking V out A, and we're forcing V out A to be at this point. And the op amp is doing that for us. It's controlling this MOSFET to change its resistance to force this whole line, because it's all connected to the minus of the op amp, to be as close as possible to V out A. And that's just the nature of an op amp. That's what it does. It'll change its output to make the plus and minus as close to each other as possible. And so what's really cool is that without affecting the path in any way, we've actually been able to not only measure, but physically and literally control how much current is flowing in this path. And because we can control it from V out A is controlled from the DAC. DAC is controlled from our microcontroller. So our microcontroller now has access to a super precise constant current circuit that can modify the brightness of the LED to exactly what we need. Does that make sense, everyone? Matthew?
What does the 10 ohm resistor do in the gate of the MOSFET?
Yeah, good question. That's usually just for stability. So people like putting really small resistances on gates of MOSFETs. Sometimes you get ringing on the gate of a MOSFET. And putting, I guess that's not a very clear drawing because that's a resistor. But if this is voltage of the MOSFET, the gate, sometimes you get like some noise on that. And so putting a resistor usually helps keep it quiet and more stable. Usually optional.
So for like when you read feature schematics, if there's a resistor with no value on it, it just indicates it's a very small resistor.
Well, you can see the 10 here. You see that 10?
Oh, I didn't. Okay.
Yeah.
Because the other ones have like letters beside them or something, or like. See.
Sorry. Yeah, so this is a 10 ohm, 100K, 100,000. You don't usually see an ohm symbol. 0, 10, 15,000, 60,000. Right. Okay, so transfer function. What does that mean? Basically, what can we multiply our input in to get our output, right? So V out A comes out. So let's clean this up a bit. So V out A comes out here, drops down. This voltage is forced here, and so we can calculate the current. So does Andre, do you want to try walking us through what that would look like?
What's going on?
So if I had, so let's call these different points in time. So let's call this VA. And then not to be confused with any of these, but we're going to call the next few points VB, VC, etc. VB, and as we said, VB is forced to this point. VB. Okay, so how does VB relate to VA? Maybe Raphael, do you want to quickly, or Andre, if you're on it, do that for a second.
VA over 5.
Yeah, so 5 was true from here to here. But you also have this, right? This is what we kind of weren't sure about before. It's very, very minor. It's just a little network of resistors. So it's one chip you can buy that has a resistor here, a resistor here, a resistor here, resistor here. So it's just a 22 ohm resistor, 22 on each thing. So there's 4 resistors here inside one package. So you actually also have essentially a 22 ohm resistor right there. Right, if I were to just move this and show it more quickly. Does that make sense? So you have 22 ohms, 60.4K, and 15K. So your actual VB is going to be VB equals 15K divided by 22 plus 60.4 plus 15. All of this times VA, right? Raphael, does that make sense?
Yeah, makes sense.
Cool. So can you give me what this number would be?
It's 15%, so just 0.15.
This is 0.15?
Yeah.
Cool. Wait, is that right? .15. Let me just double check.
You added a 22 with a like 60. You treated
Oh
it.
yeah, I added. Yeah, I thought of it as 22K.
There you go. Thanks, John. Good catch. So what would it be if I didn't draw this very well, but that's exactly right. This is a K. This is a K. So you either need to do them all in Ks or all in ohms, and it would be the same thing. So what would it be if they're all the same?
Pretty much still like 1/5.
Yeah, can you give me a decimal? It's basically 0.2, right?
Yeah, 0.2.
Yeah, so it doesn't change that much compared, and it makes sense too, right? It's only a 22 ohm compared to 60,000 and 15,000. So it's not going to change much. All it's really doing for you is this here, this path. This is an RC filter. So all that little path is doing for you is just filtering out a little bit of noise you may have. But the actual real division happens with these kilo ohms. So the 22 ohms is not going to have almost any impact. Okay, cool. So we know VB is about a fifth of VA, right? And we know that through our special sauce constant current circuit, we're forcing this pin, this VB, to be at this point here. Now, what's the current flowing through there? Matthew, you want to tell me? In terms of VB. You're muted, by the way. Matthew, I'm begging you. Please. Please, Matthew. Okay. If you don't say anything, you're agreeing to give me $100. $200. 300. I'm so glad I'm teaching this class. I'm just getting rich. 300. 400. Okay, someone else give me an answer. Easy. No trick here.
VB over 10.
Cool. So how do we relate I to A? Well, substitution, right? So we know I equals VB over 10. And we know that VB is about 1/5 of VA, right, from before. Equals 0.2 over 10 times VA. So VA times 0, maybe let's not put an X, VA and 0.02 equals I out. Agreed? Now, does this look familiar? Input times something equals output. Input times something equals output. That something is our transfer function. So now we know how to relate them. Transfer function, literally just 0.02. Great. Okay, that took us a long time. Three, what is the adjustment resolution in the output parameter? Who can tell me this? Mahmoud? And by tell, I mean walk me through how you would find that.
Adjustment resolution in the output parameter.
Yeah.
I don't know what adjustment resolution means.
Okay, first of all, what's the output parameter?
The current through the
Okay.
LED.
Cool. And how much resolution would we have of that? What does that depend on?
Oh, like the 10 bits from the DAC.
Ooh, I like that. So remember, we have a relationship now between the voltage we're controlling from the DAC, VA, and the output parameter. So if we knew the resolution of VA, we could find the resolution of V out, of I out. Do you agree?
Yeah.
Cool. So, adjustment resolution.
Do we know what's the maximum like V out A or
You tell me.
DAC ref 2.5? So I guess the max is 2.5.
That's right. Remember, this is your analog voltage reference pin that decides the output full scale. And they've told you here, this is a little hint by them, they put that DAC ref is 2.5 volts. So you know your output is going to be between 0 and 2.5. Right?
So I guess let's get the smallest division for VA first by
Like that.
doing 2.5 over 2 power 10.
So that would give us basically the little step size and voltage that V out A could be, right?
Yeah. I don't have a calculator, so
Okay, who can do this? 5 divided by 2 to 10 is 1024? Is that right?
yes.
So basically, the adjustment resolution of V out A, 0.00244. Speak up if I did the math wrong. So that means that with our DAC, we can control little increments of that amount of voltage, right?
Yeah.
So what does that mean
and
for
then
the current? Yeah, tell me.
we can put that in the equation that we made with the transfer function. And that would be the smallest. That would be the resolution of the current, I believe.
Love it. That's exactly right. So that would be all of that times 0.02. So 1, 2, how many zeros?
That's so fine.
Yeah. So you can imagine this is probably not just for like fun, you know?
Yeah. They
They're
really fucking care about this E LED.
Yeah, they are. They really want precise current control and the brightness. So does everyone understand how we got there? We know how to relate the the output voltage from the DAC, which we control from the microcontroller, through the transfer function we found, to get exactly what current that would be, right? And you can do this for any voltage, right? If I put in 2 volts here, I'd get out exactly what current is through the LED. The same way goes for the resolution. If I put the exact smallest amount of voltage I could send into the out A, I would get the exact smallest amount of current I'd get out in I out, which turns out to be 0.05 milliamps. And so if I can step my voltage up by these little increments every time from my microcontroller, I can step up the current by these little increments every time as well. And so I have super fine resolution on this. Right? Boom. All right. What is the LED VCC? Just a question at the end. Someone tell me, how would I find this?
Just
Is it
looking at
1.225?
Like zoomed into.
Say again?
Is it 1.225?
No, that's a good question. Good attempt though.
I like how you zoomed into where your hint is.
Yeah. It's been a long lesson, so let's just kind of go for it now. So feedback pin voltage. Anyone see a feedback pin? You see it right here. So what they're saying is that the voltage here is 1.225. Right? And turns out that this linear regulator is actually creating the LED VCC voltage from 5 volts. So through the regulator comes out, and the way it regulates that to stay solid LED VCC is through this feedback network. And they're saying this pin, this point here is 1.225 volts. So what does that make this point? LED VCC. Elena, do you want to give it a try?
Not really, no. This all is kind of gibberish to me now, so.
Okay. Do you know how to go the opposite way? If you had this voltage here, could you get this voltage? This is just for Vx and Vy.
Would we just use that same formula we used, I think, for like the first question?
Yeah. What does that look like?
Vy equals R3 over R2 plus R3 times Vx.
Yeah, that's right. Perfect. Good job. That's exactly right. Yeah, a good way to remember that is just the voltage across R3 will be the R3 resistance over the total resistance, right? So exactly what you said. So using this equation, we know Vy now, right? We know this. It's given to us as 1.225 volts from here, right? Do you agree? Elena?
Sorry, what was that? I was just writing stuff down.
Anyways, do you agree that this point here is 1.225 volts?
Yeah, yes, yeah.
That's because we've been told here that the feedback
Yeah.
pin voltage, yeah, and that feedback pin is attached to this point, right?
Mm-hmm.
So that's Vy. So can you calculate Vx for me now?
Sure.
And if someone else is doing it too, I'm too lazy to calculate it, so we can check to make sure we have the right answer.
Would it be 4.5?
Yes. That's right. Well done. That makes sense, everyone? So essentially we have, just to reiterate everything that's going on here, we have 5 volts coming in. This regulator is dropping it down to 4.5 volts. This 4.5 volts is used as the power supply for the LED. We have the ability to control the brightness of the LED via digital, converted to analog, analog converted down through a voltage divider, through a constant current circuit, and all of that is represented by our transfer function down here, right? 0.02. And all of that controls the current flowing through this LED. Does that make sense, everyone? So this is an example of a real-life application of when you would use a digital to analog converter, why you would use it, how you would use it, and something that is actually being used in an actual company and that people are using now as interview questions. So it took us about an hour and a bit to go through. So usually you're not going to have that much time in the interview, but I think it was a good exercise to kind of walk through the sort of things that you guys will be working on throughout your engineering careers.
How much time did you have to solve it?
You probably walked through it with me in like 20 to 30 minutes.
Oof.
But again, I kind of guessed the first one. I guessed the second one. Definitely did not get the third one. I think I got the fourth one. I think that one was I knew how to do.
Nice.
Yeah. All right. How was it?
This is great.
Very cool.
I wish you replaced Nirmani, you know?
Savage. Yeah, but it's surprising how like detailed you can go with just one circuit, right? And how like with you thought you were just doing embedded, right? You thought all you had to do was send the digital signal to the DAC and you're done. But you really need to understand how that's going to flow through to the rest of your circuit. Because if you actually, your customer comes to you and they say, hey, I'm doing a really precise optical experiment and I need to be able to control the current through my LED to within 0.05 milliamps. You need to know how to go back and create that resolution from your microcontroller through to the LED, right? And our microcontroller controls voltage, it doesn't control current. So we figured out what resolution our external DAC would need to be. We said with 10 bits, we'd get this amount of resolution. That would give us 0.05 milliamps of resolution for the current based on the transfer function, right? And we kind of went backwards in this case where we were trying to back calculate everything and find out the resolution of the LED by the end, but this would be something your customer is going to specify for you. They say, I need this. Then you can now go backwards and be like, okay, what does my transfer function need to be? What does my DAC resolution need to be? And what kind of circuits do I have available to me, right? We know the DAC. The voltage divider is something we used heavily here. We use it a lot here. We use it in our linear regulator. And then having this constant current circuit in your back pocket for whenever you need it. Then there's other little things that show up like this little RC circuit, right? We need a little bit of filtering. This RC circuit here, right? This enable pin that Faraz mentioned at the start. This is also super useful, right? You're going to need test points. See everything here, these little TPs? TP1, TP3, TP4. These are called test points. So they're literal physical little pieces of metal exposed on your circuit board that you can go with a multimeter and measure the voltage. So for a digital to analog converter where you're outputting an analog voltage, you can imagine that that's super important to have test points for, right? And they have test points for all of their analog outputs. Right? This one happens to have 8. There's a test point in everything. So there you go. Hope you learned something. And key takeaway, embedded heavily affects electrical, electrical heavily affects embedded, and they work really well together. And it's critical to be able to understand both. Right, end of my rant. 3 questions, please.
Is there anything like this in our car?
That's a good question. I don't think we have any constant current circuits, for example. There's none of this on the right. We have a DAC on our car, right? We use that to control the throttle for the inverter input. So we have a DAC. So we send digital to the DAC, and that sends an output voltage to control our motor. We have linear regulators to generate different voltage rails. We have a bunch of voltage dividers. We have filters. We have test points. We just don't specifically have this constant current guy at the end. Any good resources for catching up on the basics? Yeah, good question, Courtney. Jared has actually been running some really good electrical tutorials, and we actually have them all posted on YouTube. So if you want to take a look, I think you just have to look up Team Phantom SFU on YouTube. And I think these embedded lectures are posted, but also all of the ones Jared has done, which have covered voltage dividers, resistors, RC filters, linear regulators, MOSFETs. He's going to do op amps later. So they're a really great resource for learning those basics. And they all play well together, right? Each of them is a little building block upon which you can build a whole system. And this is something people sell, right? They make money off of this. This is literally how businesses are built. For example, this is a consulting company creating solutions like this for different startups and conglomerates and other types of companies who need solutions. So this is super useful to know. Last question.
So C13 is primarily just a speed thing?
I would say so. To be honest, I don't know 100%. I can't go ahead and hear. From what I understand is it's a feed-forward capacitor used to make the system react more quickly, because all the AC transients are going to go through here straight to the output. I'm not sure how it would work otherwise, or like if it acts as an integrator, how that affects the system, or why you would need that. But if you want to take a look and do a deep dive into it and let us know later, that'd be cool.
You do the work. Actually, one more thing then.
Yeah.
Would it be beneficial in any way, or just overkill, if you were to have like a feedback measuring pin at your VB or something to validate, or is that more of an overkill?
Yeah, that's a good question. Like, you know how we said before, what if your resistance of the load is too high, right? And you can't actually control the current to what you need. Do you just measure this pin to make sure what it is? You could. I'm not sure if that would. I think that'd be okay. At that point, I think what you would just do is put a current sensor in this path, so that you can validate it that way and get an actual measurement of what you want to control. But maybe a low-cost way to do that would just be measuring this. And it may not I don't know if it'd like be overkill because it's not going to hurt you to just shove that into an analog input pin and read it. So yeah, I think that'd be a good idea.
Cool.
All right. Thanks, everyone. Enjoy your week, and we'll chat next week as well.
Thanks for the lesson.